A theoretical physicist, C.N. Yang, was awarded the Nobel Prize in Physics in 1957. Among a host of other contributions to his field, his work with Robert Mills resulted in Yang-Mills theory, considered the basis of modern physics. He has crossed paths with the other great minds in his field, Einstein and Fermi, Oppenheimer and Teller. Here at Stony Brook, the Institute for Theoretical Physics, which he directed for 33 years, now bears his name. Dr. Yang, thanks very much for taking the time.
I'm very happy to be here.
You grew up in China, the son of a mathematics professor.
Yes.
Can you tell us a little about your early life?
I was born in central China, but I grew up in Beijing. So my primary school years and 4 years of high school were in Beijing. And in 1937, I was 15 years old. The Sino-Japanese War started, and my family moved to southwestern China, to a city called Kunming, which is famous as the end of the Burma Road. Mm-hmm. And I went to college there. In 1945, I was 23. I won a scholarship to come to the United States. So I arriving on November the 24th in New York City. Because at that time, there were no commercial traffic between China and the US. And the only way for me to come from Kunming in southwestern China to the US was to fly to Calcutta, India, and there wait for a boat, a ship, one of those troop transport ships of the American military forces, which were used to transport over 1 million American soldiers in the China-Burma-India theater from that area to the United States. So I waited for 2 months in Calcutta for a berth on one of those troop transports. And the ship was about 5,000 tons, and we went through the Mediterranean and the Atlantic Ocean, where we got into a storm, and I remembered I was vomiting so much, and I said to myself, maybe this trip is not worth it. But anyway, I arrived in New York and went to Chicago and became a graduate student at the University of Chicago.
That was quite an adventure for a young man.
Yes, it was. And of course, to come to the United States from a completely different culture was, I wouldn't say it was a shock, but it was, it required some adjustment.
Was it your knowledge of physics that got you, that sort of bridged that divide?
Yes, I had a very good education, both in college in Kunming and later for 2 years in the same university as a graduate student, earning a master's degree. My level of education in China was very advanced. Such things like quantum mechanics, I've studied thoroughly in China. So when I got to the University of Chicago, which had at that time the world's best physics department, I found that the quantum mechanics course offered in Chicago was not as deep,
really?
nor as detailed as the course I had in China. So I had a head start in some sense. And so I earned a PhD degree in Chicago in 1948.
I was thinking that when you made your journey to the United States, it was at about that time that the United States had dropped atomic bombs on Hiroshima and Nagasaki.
Yes.
How did that affect you, if at all, in your field and as a person?
It has a profound effect. You know, China was fighting the Japanese invasion from 37 to 45, 8 years. And China was very weak at that time, and it was a miserable time, and the Japanese were very brutal. You may have heard of this massacre in Nanjing.
Yes.
And nobody had any inkling that there was this new weapon developed in the United States. In fact, I understand most of the people in the US didn't know about it either.
Right.
And so the morning in August, when the bomb was dropped, when the radio announced the news, it was a great elation for the people in China because everybody knew that's the end of the misery of the 8 years of war. I remembered I came out of our house, rented house, and got onto the street, and suddenly I saw many people exploding firecrackers. You know, in the Chinese custom, if you have something to celebrate, you have hundreds of firecrackers. And then I got hold of a newspaper and then realized what happened. Of course, that was a great event for the American people, but I would say the American people did not suffer as much during the war as the Chinese people. And as a consequence of that, the happiness and the elation that was felt in China was proportionally higher.
Did you understand the physics ramifications of the atomic bomb at that time?
The general physics principle that one can generate tremendous amounts of energy by neutron collisions was known since 38 and 39. And that, in fact, even got into textbooks. But the detailed procedure by which you can do that was a very complicated engineering process. And you probably know that it was so difficult that the Germans, in about 1944 or 43, decided it cannot be done during that war. So they abandoned that project. Fortunately, they did. And in the United States, it was picked up first because of a letter Einstein wrote to President Roosevelt, but more because of the fear among the American government and the physicists especially, that the Germans might get it first. So they devoted wholehearted effort at Los Alamos to do this. It's a most important event, of course, not only for the 20th century, it's one of the great events in the history of mankind.
And I certainly don't wish to make this all about the bomb, but it's sort of coincidental that you went to Chicago, the university where much of this work was done. And one of your mentors there was Fermi, I believe?
Yes.
Tell me a little about Fermi.
Enrico Fermi was born in 1901 in Italy. At that time, Italian physics was not so great. And he was a precocious young man, and he alone lifted the level of Italian physics to world standards at a very young age. He was a remarkable person. I had said that Fermi was a person with both feet on the ground.
How so?
In the sense that he was very solid. He looks like he was a solid person, and he is. When he speculates on something, you know that it was based already on concrete thought, which he had already been thinking about. Therefore, his words carry authority, because you know that these are not the random or off the top of one's head kind of remarks. And he was a great theorist as well as a great experimentalist. You know, in early centuries, many great physicists were both theoretical and experimental. But by the 20th century, theoretical physics has gotten so complicated, experimental physics has gotten so complicated, so very few people could do both. And Enrico Fermi was the last great physicist who contributed first-class work to both sides.
How was your relationship with him?
Oh, very close. You see, when I got to Chicago, very rapidly everybody found that this young man from China was extremely well trained. So I had a very close and warm relationship with Fermi. Mrs. Fermi, the Fermis had two kids, and one of them, the older one, Nella, was college age. So the Fermis always hold a square dance party in their house, and I was there many times and got to know the family very well. Later on in 1949, Fermi and I wrote a paper together. It's called Our Meson Elementary Particles. And I was very happy to see that that paper is still referred to today, because we were the first to publish a paper saying that what is known as a pion may be a bound state of a nucleon with an antinucleon. These are probably two technical terms, but anyway, we wrote a paper together, and so I was one of the favorite students of Fermi in Chicago.
You, of course, knew Oppenheimer. You were at the Institute for Advanced Study with Oppenheimer.
Yes.
Tell me about your relationship with him.
Everybody knows that Oppenheimer became very famous because of his direction of the atomic bomb project during the war. And in 1947, he accepted the directorship of the Institute for Advanced Studies. And in 1949, he came to Chicago to give a talk about a new development in physics called renormalization. I will not explain what it is. But anyway, that was the hottest topic around that time. So I was fascinated by his talk. And I knew that starting that fall, the fall of 1949, there'll be many experts on renormalization at his institute in Princeton. So I applied to become a postdoc at Princeton. And Oppenheimer accepted me. So starting in 49, the fall, I went to the Institute for Advanced Studies. I was originally just going to be there for 1 year as a postdoc and return to Chicago. But I remained, and altogether I was in Princeton for 17 years, from 1949 to 1966. And as you know, the Institute for Advanced Studies was a well-known ivory tower in the best sense of the word. Their scholars do their research without being bothered by committee work, without being bothered by graduate students. And indeed, I took great advantage of that. That was the period, that 17 years was the period when I did my best research work.
I understood that Oppenheimer tried to convince you to replace him when he left the Institute, but that instead you came here to Stony Brook, which was barely peeking out of the ground at the time. What happened there?
Yes, what happened was the following. In 1965, first, before President Kennedy was assassinated, he named Oppenheimer as the next Enrico Fermi Prize winner. The Enrico Fermi Prize was a presidential award. It was originally awarded to Fermi because Fermi was dying, and they quickly created this prize and gave it to him before he died in 1954. And afterwards, many distinguished people who contributed to the U.S. wartime scientific work got the prize, including Beta, including Teller, etc. And probably, or very likely, because President Kennedy wanted to erase the sorrows that the U.S. meted out to Oppenheimer in the Oppenheimer hearings of 1954. So he decided to give the next one in '62 to Oppenheimer. But before that transpired, he was assassinated. Kennedy was assassinated. So then Johnson became president, and in fact, the rumors were that many of the people who were against Oppenheimer tried to convince Johnson not to give that award. But Johnson did not listen to them, so there was a ceremony, and Oppenheimer did win the award. So that was, I think it was 1963 or '64. But anyway, that was at the time. So by 1965, Oppenheimer had just had this great event of the United States government essentially saying implicitly, we are sorry,
right,
and we apologize. Now, Oppenheimer, as the director of the Institute, had great difficulties with the mathematicians in the Institute. That's a long story. I'll not bother you with the details. He was the director, but the mathematics group, which is the strongest at the Institute at that time, and still today, were unhappy with him. In my opinion, they were wrong in accusing Oppenheimer of not favoring mathematics. But anyway, they made Oppenheimer's life very difficult for many years. So one day in '65, I remember Oppenheimer dropped by my office and said, Frank, I'm thinking of retiring as director. How do you think about it? I was surprised, but I thought about it for a few minutes, and I said, I think this is a good decision. Because, I said, you have been at the Institute for a long time now, and this is the right moment, because A, there is a lull in the opposition on the part of the mathematicians against you. And in the heat of great debate, it's difficult for you to say, I want to retire. And secondly, the United States government has essentially apologized to you. This is the right moment. So he thanked me for my opinion. Then he said, I want to propose you as my successor. My instinctive reaction immediately was that I don't want to do it, because I'm not a administrative type. So I told him, I'm honored that you thought so, but I'll think about it for a few days. So I thought about it, and eventually wrote him a letter saying that while I am not sure I'll be a good director, I'm, however, very sure that I won't enjoy the life of being a director. So that's the end of that part of the story. But just around that time, a little bit before my final decision, but after he had mentioned his proposal to me, John Toll, who had just been nominated as the president of Stony Brook, came to visit me and asked me to join him in Stony Brook to develop Stony Brook into a great research university. So when I wrote that letter to Oppenheimer, I had already decided with my family that I'm going to move to Stony Brook. That was in '65.
And you came on pretty much on the promise that a great research institution would be built here, because there was none at the time.
Yes. You of course know that Stony Brook began about 50 years ago, but it was in another campus, and the real expansion started when it moved here, and the great expansion started when John Toll came in '65 and '66, and that was a great period of expansion. And I think what you see today have all, in many senses, originated with the few beginning steps that John Toll and his administration put in place.
And that you helped him with?
Yes, in some respects.
You knew also Einstein.
Yes, I went to the Institute, as I told you, in 1949. He was 70 years old at that time, and he had just retired. But he lived close to the Institute, and he would still walk to the Institute every day. He didn't drive, and he would walk to his office and then stay a few hours and then walk back. Now, at that time, Einstein's position in physics was towering. I had said repeatedly that Newton and Einstein are the two greatest physicists of all times. And but he was at that time no longer working on the things that we young people were interested in. So we didn't so much bother him. However, I did hear 2 lectures by him, and in 1951, I think it's 51 or 52, he sent his assistant, Brewer Kaufman, to me and said, you just published a paper in the Physical Review about gas, liquid, how gas became a liquid, how upon cooling. And Professor Einstein would like to talk with you about that paper.
Wow.
So I went to see him, and we must have spent an hour and a half together. And I was very much awed by his presence. I didn't get very much out of that conversation. I only remembered he repeatedly drew a curve, which was very famous due to Maxwell, a great physicist of the 19th century. And indeed, Einstein was deeply in the tradition of old physics, of classical physics. Two branches of that, statistical physics and electrodynamics, were his great forts. And using this tradition, using his deep perception in these two areas, he launched 2.5 revolutions for physics in the 20th century.
2.5?
Yes.
Which was the half?
Quantum mechanics.
Okay.
The 3 revolutions were, that's generally accepted as the greatest revolution in physics after Newton. It was special relativity, general relativity, and quantum mechanics. Special and general relativity were invented by him, essentially alone. Quantum mechanics was the work of many people, and so I count that as half a revolution by Einstein.
I'm unable to plumb the depths of physics or scale the heights of physics, whichever it is, but I wonder if you could explain to us non-physicists the Yang-Mills theory.
You know what the fundamental physics is about is to ask how matter is put together. In the 19th century, finally people realized that everything is made of atoms and molecules. In the 20th century, we learned that the molecules are made of atoms. Atoms are made of protons and electrons and neutrons. But what are protons and neutrons made of? Now we know they are made of quarks. So that is one aspect of what we do. Namely, we want to take matter apart and look at the constituents. But there's another part of the endeavor, namely how these parts are put together. The reason that they are together is because there's a force between them. Force is in daily language. In physics, we call it interaction. So the question is, what are the interaction between these constituents? Interaction of force is well known already since Newton's time. There's gravitational force. And through the 19th century, we know there are electric and magnetic forces. In the 20th century, we know there are 2 additional kinds of forces. They are called nuclear forces, which are responsible for the atomic bomb.
Nuclear forces.
Nuclear forces. And weak forces, which are responsible for such things like radioactivity. So there are now 4 types of forces. The question is, what are the precise nature of these 4 types? We know that the gravity through Newton is a inverse square law. You probably learned that in high school physics. So you might say that the basic question that one of the basic questions, one of the fundamental basic questions we face is how are these 3 other forces structured? They are not inverse square laws, but what are they? And that's where the Yang-Mills theory or gauge theory comes in. Gauge theory gives a principle which governed how these forces are structured mathematically, precisely. And when Mills, well, originally in 1918 and 1919, stimulated by Einstein, Hermann Weyl, a great mathematician, proposed what is called gauge theory. He used that to describe electricity and magnetism, and that was successful. But it does not apply to the other 2, the nuclear forces and weak forces. And what Mills and I did was we generalized what Weyl did. And that becomes a general principle of forces, of why they are these forces, including gravity. And that principle is now called the gauge principle. And the gauge principle's detailed mathematical structure is what we wrote down in 1954. At the time that we wrote it down, nobody believed that it was important, and we didn't know it was that important, but we said that this is a beautiful idea, and the mathematical structure is very elegant. So we published a paper about it. And then 20 years later, various experiments showed that that in fact was approximately the right direction. Then after struggling for another 5 years, it became clear that it's not just approximately right, it is exactly right. So that became something which is now the universally accepted principle of how these forces are formed.
1954.
Yes.
How do you feel about that? The fact that 50 years later, something that you created, that you propounded, has been so fundamentally has so fundamentally changed your field?
Well, of course, I feel good about it, but I tell my students that the structure of everything oftentimes has hidden beauty in it. If you can sense vaguely some of this beauty, do not let go. The reason that in 1954 Mills and I were able to do it, as I told you, it was not in agreement with experiment, and nobody believed us. But we saw the beauty of the structure, so we wrote it down.
The elegance of the structure.
That's right. Oh, by the way, I should add the following, and that has something to do with Stony Brook. Okay, this Yang-Mills theory was published, and gradually, originally people didn't believe it. Gradually, more and more people see the beauty of it, so people began to work on it. But it was only in the 70s that it was confirmed by experiment. And so by the 60s, there were not many papers, but I would say every year there'll be 10 papers, 20 papers about it. And I came to Stony Brook in 1966. And one day, it must be 68 or 69, I was giving a talk. I was giving a lecture. No, I was giving a course on general relativity. It's a graduate course. And I wrote down on the blackboard one long formula, a famous formula called the Riemann tensor. Riemann was one of the greatest mathematicians of the 19th century. And the Riemann tensor has something to do with Einstein's gravity theory. So I copied down on the blackboard this long formula of the Riemann tensor. As I was copying down, it suddenly flashed through my mind that the structure of this Riemann equation is very similar to the equation that Mills and I had written down. When we wrote it down in 1954, we didn't notice, we were not doing general relativity, so we didn't notice there was any similarity. But during that lecture, I found that they were very similar. So after the class, I went to my office and checked in detail. And sure enough, they were not just similar, they were exactly the same if you define some quantities correctly. So I was a bit excited, but I didn't understand it. And so I went to see Jim Simons. Jim Simons, as you know, was the young department chairman of mathematics at Stony Brook. And he was a great geometer. So he knew Riemannian geometry very well. So I went to his office. We were still in that old red brick building, both his office and mine. So I said, Jim, here's the rebonding formula that you are very acquainted, very familiar with. And some years ago, Mills and I wrote this formula. Look, they are very similar. And he thought about it for a while. He said, yes, that's not strange. They are both fiber bundles. So I said, what's a fiber bundle? So he gave me a book written by a famous Princeton mathematician called Stinrod. It's called Fiber Bundles. So I went back with the book, and but the book was impossible for me to understand. The mathematicians have a tendency to write very dry, very abrupt statements. They are precise, but there is no flesh to it. So it's very difficult to, it's all bones, and it's impossible to understand. So I didn't understand. So I went back to Jim and said, look, this book is useless for physicists, but we want to understand what this fiber bundle business is about. And could you explain to me what it is? He said the fiber bundles is a new thing in mathematics too, but earlier than in physics. Starting in the 40s, there were already many papers in mathematics in fiber bundles, and it's now an important branch of geometry. And so I said, could you give us some lectures understandable to theoretical physicists? He said yes. So he gave a series of luncheon lectures, very informal. There may be 10 of us, faculty and graduate students of the Institute of Theoretical Physics here at Stony Brook. And as he must have talked for about a whole month, and that was very useful for us. So at the end of that, we decided to give him a gift for this series of lectures. So we chipped money together and decided to buy something for him. And I went to Irving Krah, a mathematician whom I knew very well. I said, Irving, we want to give Jim a gift. What should we buy? He said, Jim cannot spell. Give him a dictionary. So we bought a big dictionary and gave it to Jim. And he told me recently that he's still using it. But what we learned from Jim in those lectures were very important, not only for me, not only for Stony Brook, but in fact, it launched a new trend. And that came about this way. After I understood the gist of what the mathematicians were doing with fiber bundles, I realized indeed both general relativity of Einstein and gauge theory were fiber bundles. So I wrote a paper with T.T. Wu of Harvard immediately after that, in which we explained in detail the relationship between the mathematicians' ideas and terminology and the physicists' ideas and terminology. And so we made a little dictionary. The little dictionary had only maybe 15 entries. On the left side are the physicists' terminology. On the right side are the mathematicians' terminology. And there was an exact correspondence. So we called it a dictionary. But there's one item which physicists used repeatedly. Its technical term is called source. Source actually was due to, the idea of source was due to ampere. You know the electric current, 3 amperes, 5 amperes?
Yes.
That was named after the great French physicist, 19th century physicist, Ampere. And now, in physics, Ampere's idea of a source was a crucial concept. So we have to have that in our dictionary on the physics part. But on the mathematics part, I went to ask Jim, what do you call this? He said, we don't deal with this concept. So we left that the blank. So it's a dictionary with maybe 15 entries on one side, 14 entries on the other side.
And nothing to correspond to source.
Yes. But then E.C. Singer from MIT, a distinguished mathematician, came to visit. I had known him, so I gave him a copy of our preprint. And he looked at it, and there's this blank. So he thought about it and decided that is a very interesting concept, and they should deal with it. They somehow, in their 20 or 30 years of dealing with fiber bundles, had never touched on this idea. So he went to England immediately, and he was a great collaborator of perhaps the greatest mathematician today in Great Britain, Michael Atiyah. It's now Sir Michael Atiyah. At that time, he was not a sir yet. And so they looked at it and found that this concept that they never used, but we dealt with since Ampere, was most interesting. That became now a new branch of mathematics. So they wrote a paper. And because of the prestige and the fame of Atiyah and Singer, many young mathematicians all began to look into this. And now it is a thriving branch of modern mathematics.
What do they call it?
Well, there are many names. In particular, a student of Atiyah called Donaldson did the pioneering work in it. So it's called the Donaldson theory. But all those are related to that blank spot. So in some sense, you know, in the first half of the 20th century, physics and mathematics were divorced. In early centuries, physics and mathematics were in close collaboration. But in the first half of the 20th century, the mathematicians became more and more abstract. They, in fact, were very happy that they, in fact, one of them wrote an article saying that the greatest contribution, the greatest achievement of 20th century mathematics was that it finally liberated itself from the shackles of physics. That was by a famous mathematician. But with this fiber bundle business, the mathematicians and the physicists are now coming together again. So if you want to say, how did that coming together come about? I would say that it has something to do with me and Jim and that blank spot in that dictionary and with the Stony Book. So we are very happy that Jim continued to be interested in physics and math, and you know now he's a billionaire, and he just announced he would give $25 million to Stony Book. That's great.
Yeah. So you, I mean, you have, this is just another way you have made connections in your life, not only connections having to do with matter, but also interdisciplinary connections as well.
I moved back. My former wife passed away in 2003. I moved back to Beijing. When I was growing up in Beijing, as I told you before, my father was a professor at the Tsinghua University in Beijing, one of the most prestigious universities in China. And so I grew up on that Tsinghua campus. In 2003, after my former wife passed away, I moved back to that campus, and now I'm a professor of physics on that campus. And Jim and Marilyn came to visit us in 2001. That's before I moved back. I was already visiting that campus very frequently, and Jim came, and I remembered what happened precisely. After his visit, I came back and he came back, and I visited him in his office here in Sitoket. I said, what's your impression of China? Oh, he said he was very happy with the visit. He said, I figured the greatest problem in the world today is poverty. And here I see 1.3 billion people pulling themselves out of poverty by their own bootstraps. That's a great contribution, not only to themselves, but to the world. So they deserve our help. What do you need? So I said, we have many visitors in Beijing, but the housing was lousy. How about helping us to have some visitors housing? So he gave $1 million, and now that complex prices are still cheap in China. So that $1 million is sufficient to have 9 very nice apartments built. And it's called Chen Simons Hall, because one of his great contributions to math and physics was a paper he wrote with Chen in the 1970s. And he and Marilyn recently went to Beijing and opened that hall. So I think that through the math-physics connection, there is now a Stony Brook-Tsinghua connection too.
I wanted to ask you, you mentioned that when you came to the University of Chicago from China, you actually already knew some of the things that they were teaching at the time. You were very well trained. How do you see the differences in education in the United States and in China today?
That's a very important question, and I've been reflecting on that. I think there are very fundamental differences, and these fundamental differences show up on each side, good points and bad points. You know that the newspaper said that President Bush just appointed a committee to study how to address the problem of mathematics education in the primary and secondary schools in the United States. Why? Because in many high school student mathematics examinations, international examinations, with maybe 30 nations, the U.S. always is near the bottom. It's the Asian countries that are at the top. So of course that gets the educators and the mathematicians worried here, and that's why this appointment. Why? Why is it that the U.S. High school education in mathematics is not as good? It's because the whole educational philosophy and system are different. The kids here are more treated as adults, even though they were young. In China, if you have a 8-year-old child and say you should do homework, he or she would just go to do the homework. Here, if you have an 8 or 9-year-old child, and if you say you should do homework, he or she would say, I don't want to do it. Why not? It's uninteresting. It's boring. The concept that doing homework might be boring does not exist in China. So if you ask a child to do it, he would just do it.
Is this a matter of discipline or something?
Yes, it's a discipline which is in the air, so that the concept that a child would only do something that he or she is interested in does not exist. So that's the difference. Now the consequence of that is that the kids are well trained. They do lots of mathematics exercises. Okay, so that means the Chinese system is good? No, because if you go to China, they're all discussing this Chinese system is no good. All the kids are trained too much. A, they have no free time and they cannot develop other interests. B, they have the tendency to become robot-like. They don't think for themselves. So they are discussing ad infinitum how to change that system to be more like the American system. So after you have observed both these two, you realize that it's a very complicated thing. It's in fact, if President Bush asks me what this mathematics committee can do, I would tell him they won't be able to do anything. Because it's not the educational system, it's the whole society. It's the whole value judgment. It's whole idea of how you educate. The philosophy behind education is different. Mm-hmm. And so in fact, I believe that all that one can do on each side is to make small changes so as to, most of the kids here are not interested in mathematics. I would say that's okay. There's no reason for so many kids to be interested in mathematics. But the system must be such that for those who could be interested, who could in fact be extremely interested, you must provide the opportunity for them to get into it. On the other hand, in China, I would say that don't train all these kids all the time. It's too strict.
Lighten up.
Yes. So I think a comparison of the educational system, the educational philosophy in the Orient and in the United States is a very interesting and very deep subject.
Given all that you've said, why would a student in China come to Stony Brook to study?
Oh, mostly because graduate school in the United States is the best in the world today. We were talking about in the last few minutes about the primary and secondary schools. Right. When it comes to graduate education, the best U.S. Graduate schools are absolutely the best in the world. So I always say that if you have a bright child, the best thing is for him to get a good high school education in China, a college education in China, and get a good graduate education in the United States. I myself benefited exactly from that. I had a very good college education in China, where the professors are very devoted, they are very responsible, they lead you through difficult things, go into great depths, and covering large areas. That's why when I came to Chicago, I had a tremendous advantage compared with my fellow American graduate students. But on the other hand, when I came to Chicago, I learned how to explore the frontiers, how to be creative in your thinking about the frontiers problems. So I got the best of both worlds. And I think that is, I was fortunate, and I would recommend that to any young person who especially is interested in the sciences.
I think this is a good note to turn it over to our audience and find out if there are questions in the audience. If you'd step up to the microphone if you have a question for Dr. Yang.
You mentioned earlier that as time went on, experimental and theoretical physics grew apart because of growing complexities within each of them. I'm curious how you yourself decided which one to go into, or did it just sort of happen naturally with the work you were doing?
Experimental versus theoretical physics?
Yes,
how they grew apart, and how did you adapt to that?
No, how did he actually decide to go into theoretical physics?
Why did you decide to go into the theoretical branch?
As I said, experimental and theoretical physics have both become so complex by the mid-20th century. It's almost impossible to be an expert in both. And as I said, Fermi was the last physicist who made first-rate contributions to both sides. Now, I myself, when I came to the United States, I knew that I had a very good grounding in theory. I also knew that I had almost no knowledge in experimental physics. So I said I must broaden my educational basis. So I decided I should write an experimental thesis here. And so I worked, in fact, at Chicago for some 18 or 20 months in the laboratory of Professor Allison. Allison was making at that time, a large accelerator. It's about the size of this room. It's a 400 kilovolt Cockcroft-Walton circuit. And so he had maybe 5 or 6 graduate students, and I became one of them. But quickly I learned that I'm no good at experimental physics. When things go wrong, I do not know why they are wrong. And I also oftentimes turn the wrong knob and do some very bad things to various things. So my fellow graduate students were all a little bit worried when I get close to any equipment. But we were on good terms because I could solve theoretical problems for them very easily. But anyway, after 18 or 20 months of work, I was very frustrated because Allison gave me a problem, and the experiment I was doing on that problem was not going well. And one day Teller came. I had been in contact with Teller in theory, and Teller said, I understand your experiment is not doing well. I said, right. He said, why do you stick to experiment? You had already written a paper, a short paper in theory. I can sponsor that as your thesis if you make it a little bit longer. So I said, thank you very much. I have to think about this, because it was not according to my plans for so long. Thinking about it for a few days, I finally went back to him and said, I accept your suggestion. And that was a very important thing in my life, namely to learn what I'm good for, what I'm not good for.
Any other questions?
I have a question, because both of Stony Brook and Tsinghua University are very great universities in the world. And as a professor, you have taught all of the students in both universities. And how could you compare the students in both of universities? One is in America and another is in China. Thank you.
Comparing the students in China at the college level with the students in America at the college level?
Yes, I mean undergraduate.
In undergraduate?
Yeah.
Yes. How would you compare undergraduate? You spoke of...
That's a very important topic, especially since I have some first-hand observation. I taught twice in Stony Brook, freshman physics. And I taught for one semester in 2004 freshman physics at Tsinghua University. So I have a first-hand knowledge about the freshman students in physics here and in Beijing. Tsinghua, of course, is one of the most difficult to get into universities in China. And so I found that there are two differences. Difference number one is that the students in Tsinghua are almost all very well trained. They did lots of exercises in high school. So such things like analytic geometry or trigonometry is no problems for them. Here, at least half of my students here were not well trained in analytic geometry or trigonometry. They know the definitions, but they cannot manipulate because they didn't do enough exercises. So the first difference is that the high school training in China is much more rigorous than here. The second difference is that the students in China, in Tsinghua University, were very mature and very motivated. They knew they have to work hard. They sort of appreciate that what they want to do, and they go full force at it. For the Stony Brook students, I would say that at least half of them were still sort of wandering around without any specific aim in life. This is, I've thought about this. This is, again, a product of the difference of the two societies. Now, you cannot say which one is necessarily better. The Chinese system is better in training a lot of people who would mature, who would get channeled into some way of life which would make them useful citizens. But the American system is more free. And so therefore, the people's outlook on life, on everything, is less restrictive. And the best of them are given enough opportunity so that they can prosper. Look at Bill Gates. Bill Gates is able alone to create trillions of dollars, not only for his company, for the whole world. So that kind of innovative spirit, of free spirit, is the kind of things that the United States educational system and society is good at fostering. And that's true all over the world. I think the Europeans, the Japanese, all marvel at the great success of the United States system, which produced all these tremendous innovations and, as a consequence, wealth.
Okay, thank you.
Questions?
Professor, you said to sense the beauty is important in the scientific research. I want to ask whether you have any tricks to sense the beauty. Can you tell us some?
You said the importance of sensing the beauty or the elegance in scientific work. Do you have any tricks that help you to spot the beauty or the elegance?
The direct answer is certainly no. I think for a young person, it is important, and that the American system is good for this. to allow oneself to be interested in quite a number of things, and to perceive some things, some areas, some directions that he or she is particularly interested in. And if a person at a young age could latch onto something that he or she is interested in and fully develop that, that may be the way he or she would find the elegance, the beauty, the usefulness of some things. The Chinese system is not good for this. The Chinese system has too much of a tendency to impose what the children, what the school, what the society want the young person to look at, and discourage him or her to branch out. The American system is better in this respect. So it's, I think there are good aspects and bad aspects of each system when you choose to discuss different directions of what you want to push.
Dr. Yang, thank you very much.